Okay, so we finished our example talking about these principal moments of inertia, that T-beam. We found Ix, Iy, and Ixy specifically equal to 0. Well, let's talk about what is that relative to? I just told you their maximum minimum. It's relative to inclining our axes. So rotating our axes here is what we are dealing with when we're talking when it's not at a maximum minimum. So our first learning objective is expressed that the principal moments of inertia means these are maximum minimum and occur at an angle of theta p. And we'll draw some pictures here. And then for today's other learning objective, just understand that the principal moments of inertia are functions of Ix, Iy, and Ixy. So even if Ixy isn't equal to 0, we still have to go through and we have to find Ix, Iy, and Ixy, just like we have done on that previous example here. So if we take a look at what I'm talking about here, and we're going to draw, actually, let's go off right now and let's draw this picture here. I'll leave it kind of there on the far left. But for our principal moments of inertia, if we have a shape here, and looks very similar to that shape that's over there on the left-hand side, and this is one of the examples from the textbook. And they have an X and a Y axis about the centroid of that shape. So let's go ahead, we'll put an X axis right there and a Y axis right there. What they're talking about is, now on this one, about that X and Y axis right there, do we have symmetry? Is it symmetric about the X axis? Is it symmetric about the Y axis? It's not. Remember, symmetry is a mirror image, right? It's the exact same thing. Now, this one would have like a line of symmetry, I think at an angle would be its line of symmetry, right? If we angled our axes. And so that's what we're looking for, is these principal moments of inertia. If we take that and we rotate our axes, and so we go to here, that is actually going to be where we find I max. And then the I min, the other one, is actually going to be 90 degrees away from I max. And the angle that we rotate to get to I max and I min is called theta p. Oh, and actually it's not, let's not draw it up there. Let's follow the same sign convention as the textbook. So the textbook, this right here is going to be called theta p1 and is always from the X to I max, and it's going to be counterclockwise is positive. So if we go from the X axis to I max, that would be a positive theta p, that way theta p1. This angle down here is going to be called theta p2, and that's always from X to I min, to where that I min axis is located. And again, counterclockwise is going to be positive for theta p1 and theta p2. Now, theta p1 and theta p2 are technically redundant. So theta p1 plus theta p2 is equal to 90 degrees. So if we find one of them, if we can find theta p1 or if we can find theta p2, then we can solve for the other one. And actually, we are going to use something called Moore's circle to solve these problems. Which we probably won't get to today, but we will definitely get to on Monday, which is the topic for Monday's lecture, is Moore's circle. For today, I will point out, though, that in your textbook, if you want to find theta p, for example, right here, Notice that it's a function of IXY, IX, and IY. So we have to find IX, IY, and IXY if we want to find theta P. This is equation 1010 in your textbook. We're going to use Moore's circle for this one. Same with Imax and Imin. They give us an equation for Imax and Imin. Again, it's a function of IX, IY, and IXY. I don't really care. We'll talk about where this function comes from, but we're going to use Moore's circle to do all of this stuff, which is a geometric way of doing all of this stuff. But those equations are in your textbook there as well. Okay, so the other thing that we can do with also Moore's circle is we can find, if they give us, an x-axis and a y-axis here, they're not asking us to find the principal moments of inertia or the maximum minimum, but they're just telling us, hey, if we give you this angle here, say a 20-degree angle, we want you to be able to find the moment of inertia about any axis. And they typically call those the U and the V axis. And we'll talk more about this. For now, I just want us to understand that these are also IU, IV, and IUV. They're also functions of IX, IY, and IXY. And then, of course, the angle that we rotate there, that's our 20 degrees would be our theta for this particular problem. So that's another function in your textbook that we can use, but we will do this using Moore's circle is how we're going to do all of this stuff here. So let's take a look at, for today's topic, the homework problems that you have. Actually, you're going to see that a lot of them don't actually involve rotated axes, right? So the theta P is a rotated axis, and theta P is a rotated axis at this angle that gets us to maximum minimum. So P stands for principal, and then theta is just any inclination angle, any rotation angle to get us there. Now, this one, they're just asking us to find IXY. Our example that we did last time, X and Y were at the centroid of the shape. X and Y do not have to be at the centroid. Notice that this one is asking us for an X-axis and a Y-axis over here. Use whatever axis they give you. Don't always go to the centroid, right? It's whatever axis they give you is the axis that we're going to end up using. So if we have a void, in this case, can't we find about the centroid of the rectangle? Don't we know we could call that like X prime 1 and a Y prime 1, and we could find IX prime is equal, for segment 1 would be our 1/12 BH cubed. And then we could do the whole parallel axis theorem stuff to find the, to do this d sub y and d sub x stuff in there. And then if we look in the back cover of the book, we will find for a circle here, our IX prime for segment 2 is equal to, where is it? It is equal to 1/4 pi r squared. Or no, pi r to the 4th. So we could find 1/4 pi r to the 4th, and then we would do our parallel axis theorem, right? So we'd find IX1 would be our IX prime 1 plus A1 times a d sub y1 squared. And then we could do the same thing for the circle. IX2 would be equal to IX prime 2 plus A2 times a d sub y2 squared. And so we do the parallel axis theorem for each segment. And then our IX for the whole thing, because it's a void, IX1 minus IX2. So we subtract them in the end because it's a void there. So everything is the same. So even if it's a different shape like a circle, we do have to look up those equations in the back of the book here. We could find that equation for IX prime. But the process is essentially the same. Okay, and then here's a homework problem where they are asking us to find IU, IV, and IUV. Well, the first thing that we have to do is we have to go through that whole parallel axis theorem to find Ix, to find Iy. Now in this one, we do have symmetry on the y-axis, don't we, that they're asking us about. And so we would be able to tell that Ixy is equal to 0. But we have to do all this stuff first. And then what I would encourage you to do is we'll do this using Moore's circle instead of plugging in the equation into the book there. And then here's another one actually where they're asking us specifically to find the correct Moore circle and then determine IU, IV, and IUV. So let's jump into actually the start of our last example. We're going to use this example on Monday as well. And we're going to go through the whole process, just like the homework problems where they give us the dimensions of things, but then we got to work our way all the way through to find theta p's and IUs and all of that stuff. So let's do a nice big picture here. I'm going to take up like half of, I'd recommend doing this like on half of a page if you're like working on an 8.5 by 11. We have a shape that looks like this because we're going to annotate in the given information so we don't have to draw it a couple of different times. So it's kind of shaped like a C here. But the bottom of the C is shorter than the top of the C right there. And then they give us some dimensions here. Like they tell us that this distance right here is 160 millimeters. The whole height of this thing all the way from the top to the bottom is equal to 200 millimeters. The horizontal distance along the base here is 120 millimeters. The height of this segment here is 40 millimeters. Same with this segment up here, 40 millimeters. And the thickness of this piece in here also equal to 40 millimeters. So give us all those dimensions. They also tell us where the X and the Y axis is located. And so the first example we did it for the centroidal axis. And sometimes you have to, if the problem tells you to do it for the centroidal axis, you do it for the centroidal axis. If the problem tells you to do it for the X, Y axes that are given, then you got to make sure you don't do it for the centroid and you do it for the X, Y axes that are given. And so we're going to do it for X, Y axes that are located at the bottom left corner of that shape right there. And so there's our X, Y axes, and they are asking us to find for this problem. Can I write it off over here to the left just so I have more room later? So for the X, Y axes that are given, for part A, they want us to find theta P, I max, and I min. And then for part B, they want us to find IU, IV, and IUV when theta is equal to 30 degrees going counterclockwise. Okay, so it had nothing to do with what was on the slide right there as to what we're doing with this example, right? It just happened, the slide just happened to be right there. So let's look at our solution here. We're going to start, we need to find Ix, Iy, and Ixy. Before we can even find theta P, I max, and I min, we need to figure out what is Ix, Iy, and Ixy for this shape here. So we're going to start with the table. Is going to be the first thing, and this table is going to include each segment. And so we're going to have like segment 1, segment 2, and segment 3. And then we're going to find B, and we're going to find H. We're going to find the area. And then we'll also need to find in here our Ix prime. And so like Ix prime, we know for this one is 1/12 BH cubed. We're going to need Iy prime, which is 1/12 B cubed H. And then we're also going to need D sub X and D sub Y. So those are all the things that we need to find for our problem here. And in order to do those, we need to figure out how we're going to break this up. It doesn't really matter how you break this up. I could make like this line up here. I could do it vertically right here. I could do it horizontally as well. It doesn't matter. However I want to do it. I'm going to go ahead and do this. So there's going to be my segments. And so segment 1 is going to be just this rectangle right here. I'm going to call that Ix prime 1. And then that would have a Y prime 1. I'll call this top segment up here. This is going to be X prime 2. And then going straight up would be my Y prime 2. And then the last segment down here, X prime 3 and Y prime 3. And so for each of those segments, now we can start figuring out what is B and what is H. Well, for segment 1, isn't B equal to 40? H is equal to 200. For segment 2, B is equal to just this dimension right here. That's our B for segment 2. And isn't that 140 millimeters? It's 160 all the way across the top. So 140 millimeters. So 140. The height is 40. And then for segment 3, the B is going to be 80 and the height is going to be 40. And so I found B and H and A, and now or B and H for all 3 segments. Now we can find the area. So this one is 8,000. The one down here is, the next one is 4,800. And then the next one is 3,200. Let me erase that line right there so we can see where this column is cut off.
For the
yes.
Segment 2, it's 120 millimeters, not 140.
Oh, 100 and, oh yeah, because 160 minus 20 is not 140. Yes, thank you.
Minus 40.
Yeah, minus 40, right? So this should be 120 millimeters. That's right there, should be 120 millimeters. And then my area makes sense, doesn't it? 120 times 40 is 4,800. Thank you. Thanks for catching that. Okay, and then we can plug in these numbers. We have B and H, and all we have to do is plug them into Ix prime, the 1/12 BH cubed equation. And so we actually get 26.67 times 10 to the 6th. For segment 1, we get 0.64 times 10 to the 6th. For segment 2, we get 0.427 times 10 to the 6th for segment 3. And then we plug in B and H into Iy prime. We end up getting a 1.067 times 10 to the 6th. And these are all going to be in millimeters to the 4th and millimeters to the 4th. You could have converted things into meters if you wanted to do that. Really doesn't matter. The segment 2 for Iy prime would be 5.76 times 10 to the 6th. And then Iy prime 3 is a 1.71 times 10 to the 6th. Now, how about dx and dy? Dx, remember, this is the distance between the blue axis and the red axis. So this right here would be dx for segment 1. This distance here would be dx for segment 2. And this distance here would be dx for segment 3. So dx for segment 1 is going to be 20. Dx for segment 2, isn't that going to be equal to 40 plus half of 120? Right there, so 60 plus 40 is 100. Dx for segment 3 is going to be 40 plus half of this b. What is b for segment 3? B3 is 80 millimeters. So wouldn't it be this 40 here? Let me do it in purple. So we go 40 is that distance, and then this distance right here would be 40 as well. So that one is 80. Oh, and then what about the signs on these? Note the signs, remember, on dx and dy are all going to be positive for this example. Because all the x prime, y prime axes or let's say all the x prime, y prime origins have positive coordinates in the x, y system. Right? Doesn't this, let me highlight it here. Doesn't that point right there, the only point that's highlighted on our picture, with respect to the red axes, isn't that a positive x and a positive y coordinate? This point right here, positive x and positive y coordinate with respect to the red coordinate system. Positive x, positive y with respect to the xy system or the red coordinate system there. So then dy's are going to be the distances between the x-axes. So dy for segment 1 would be the distance right there. That's dy for segment 1. dy for segment 2 would be all the way from the top up there all the way down. That would be dy for segment 2. And then dy for segment 3 would be this little distance down there. And so that would be 100 millimeters for segment 1. Segment 2 would be 180. And segment 3 is going to be equal to 20. Now we can find Ix. Ix for segment 1 is going to be equal to Ix prime 1 plus A1 times the distance between the x-axes. That's a y distance, dy1 squared. We would find Ix for segment 2 would be Ix prime 2 plus A2 times a d sub y2 squared. And then Ix for segment 3 would be Ix prime 3 plus A3 times d sub y3 squared. We could add all these up. Ix would be Ix1 plus Ix2 plus Ix3. And we're going to find a value here of 264.57 times 10 to the 6th millimeters to the 4th. We could do the same thing for IY. IY1 would be equal to IY prime 1 plus A1 times D sub X1 squared. IY2 be equal to IY prime 2 plus A2 times D sub X2 squared. And then IY3 would be equal to IY prime 3 plus A3 times D sub X3 squared. The problems we're getting into right now are very different than most of the rest of the semester. When you think about most of the rest of the semester, it's all about free body diagrams and summing forces and summing moments. This last topic, the moment of inertia stuff, is more along the lines of the centroids, very mathematical, isn't it? We still need these pictures. We still need the pictures of our shapes and be able to label the distances on these pictures, but it's a very methodical process, right? So focus on that, the methods and the steps that you have to take when you're preparing, when you're doing the homework and when you're preparing for the final exam. So then we can find IY would be equal to IY1 plus IY2 plus IY3. And then we're going to get a number here equal to 80.23 times 10 to the 6th millimeters to the 4th. And then we could also find IXY. IXY for segment 1 is going to be IX prime Y prime for segment 1 plus A1 times D sub X1 times D sub Y1. Now we don't put in our table X prime Y prime 1. What is X prime Y prime for segment 1? And Daniel Thorne, I was going to call on you, but you just missed the front row. You were in the front row last time. Let's see, who else is here in the front row? P and S, or actually, why don't we just go, oh, P and S, oh, I saw somebody. I think it's Jaime Salazar, or maybe Jamie, I'm not sure.
It's Jamie.
Jamie.
I'm really not sure how to find IXY prime. I'm still a little confused on that.
So if we have this is for that big rectangle, right? This is for just this rectangle for segment 1, about the centroid of just that rectangle right there. So X prime 1 is right there, and Y prime 1 is right there. Does that help at all?
A little bit. I'm still slightly confused on it, though.
Do we have symmetry?
Yes.
So anytime we see symmetry, that means that IX prime Y prime, so about that central axis, is equal to 0.
Okay.
Okay, good. Thank you for helping me work through that. That's really important, and it is difficult to understand because you're like, but we're finding it about the red axis, or but there's other issues going on, right? And so yes, anytime, basically X prime Y prime is always going to be equal to 0 because the axes about the centroid of that segment is equal to, or because the axes are symmetric, and so it's equal to 0. So yeah, so this is equal to 0 right here, and so we'll find IXY1 is going to be 0 plus, now the whole thing, IXY1 is not 0 though, because we have 0 plus the area for segment 1, which is 8,000, times dx1, which is 20, times dy, which is 100. And so we actually find that IXY1 is equal to 16 times 10 to the 6th millimeters to the 4th. Now this is about, so that would be this segment, but about this axis down here. about the red axis, right? So this is for that one, but the blue axis is 0, but the red axis is not equal to 0. Okay, and so then, so I max would be Ix and I min. Well, for the only, so with regard to that question, only the Ix prime and Iy prime would be max and min, but not the X and Y for the whole thing, because we see we do have an Ixy for segment 1. Now, Ixy for segment 2 is going to be Ix prime Y prime for segment 2 plus A2 times a D sub X2 times a D sub Y2. D sub X2, D sub Y2 here. Now again, this will be 0 because it's about the centroid of segment 2. And so we're going to end up with a 0 plus A2, which is 4,800, plus D sub X2, which is 100, times 180. And so we're seeing here, even though the X primes, Y primes are 0, the Ixy is not 0. They're still significant. This is 86.4 times 10 to the 6th millimeters to the 4th. And then Ixy for segment 3 is going to be equal to Ix prime Y prime for segment 3 plus A3 times D sub X3 D sub Y3. And so that the X prime Y prime is 0 again. And so we're going to end up with a 0 plus A3, which is 3,200. DX3 and DY3 are 80 times 20. And so we're going to end up with 5.12 times 10 to the 6th millimeters to the 4th. And now we can find Ixy is going to be Ixy1 plus Ixy2 plus Ixy3. And so that's going to give us here 107.52 times 10 to the 6th millimeters to the 4th. Let's highlight the numbers that we're going to need. So we need Ix. That's the 264 number. We need Iy. That's the 80.23 number. And we need Ixy. That's the 107.52 number right there. So remember, part A was theta p I max and I min. We haven't even gotten there. Right? We spent like this whole class just finding Ix, Iy, and Ixy. What we're going to do on Monday. And so any homework you have where you have to do theta p or you have to do IU, IV stuff, let's wait until Monday and we'll use Mohr circle to finish this, which is what we will spend all the time on Monday doing, is finding part A, which is theta p, I max, I min, and then part B, which is IU, IV, and IUV to solve for that. We could jump into Mohr circle, but in like the 2.5 minutes that we have left, but I would imagine that you all would appreciate not doing that at this point in time on a Friday afternoon. So why don't we go ahead and call it right there.